Hello there. Let's discuss what is called resonant electric circuits. So it's the same LRC circuit that we have been talking about, and this is the AC circuit. This is a voltage source, and then there is a self-inductance in the circuit as an element here. This could be a coil that dominates the self-inductance part. And then you have a resistance. This is the net resistance, the entire circuit is over there. And this capacitance, the net capacitance, the whole circuit. Okay. So this is also called series LRC circuit. Or is resonant. We're going to talk about what it means to be resonant. Okay. So this has a couple of things we're interested in. We're interested in time much greater than L over R. Okay, and we'll see why that is the case. Okay, we'll see how why that is the case. So that's one thing we're interested in, and another thing we're interested in is, and we will see this again. That 1 over square root of LC is greater than this R over 2L. So we have these two conditions. So in this condition, what happens is the current, if you solve for this circuit, we will do that. You'll find that the current goes as actually is going to be some amplitude value, actually E0, this E0 divided by impedance, which we're going to write at Z, which is a function of L, R, and C. L, R, C, and the omega, the angular frequency. So it's a complicated quantity, okay? And it's a cosine omega t plus some phase, and this phase phi, tangent of phi, is equal to well, I've just worked out earlier, and so it's going to be R omega L minus 1 over omega C. Sometimes you kind of write it like omega L over R minus 1 over omega RC. Okay, so you can actually find this. The resonance of this current quantity current corresponds to what this Z looks like. This Z is actually a square root of R square, this quantity plus that quantity square. So as if you write this as you write the numerator and denominator like this. So if you imagine a triangle where this size is omega L minus 1 over omega C, and this side is R, and this is 90 degrees, and this is phi, then this side will be Z. Okay, and so you can actually write down phi, you can expand, you can have cosine phi and sine phi coming out. You can use this triangle. So this triangle is not it's just for mnemonic, okay? This is just mnemonic triangle. Just to remember that I could have done some other ways, P and B. So this much in P and that much in B, and then I can actually have a formula for tangent of E, and once you fit that formula, you can get all the other trig functions from it. Okay, so this is Z. So you can see that if I were to not ignoring this, ignore this part, which is oscillating, and you just look at this part. So if you look at the current will be for given all of this, for fixed R, omega, L, and C, when the current versus time, if you do it, it's going to be so it's going to be go with time periods will be like from here to here will be one time period. It's going to be 2 pi over omega, because it's angular frequency. That will be time period, and then it's going to be in a like this, between this and that, right? So this will be so let's call it I0, and this will be minus I0, and I0 will be stand for E0 over the impedance. So like impedance, like a resistance. So, but this thing depends on omega and things like that. So if you plot this I0 is a function of omega frequency, and all these things are L and C. So if you fix these guys, so if you have a circuit, you have to fix this guy, and you vary omega. So omega in the source, you vary it, then you will find that I0 will vary. I0 will vary with omega. So when omega is 0, this is 0, and you can see this goes to infinity. So 1 over infinity, so Z goes to infinity, so current is 0. So this is 0. So it's 0 over here. Say omega is infinity, then this guy dominates, and so Z goes to infinity. So omega goes to 0, Z goes to infinity. Omega goes to infinity, Z also goes to infinity. So in these cases, I0 will be over here, will be very small. So in between, somewhere it's going to actually have a single peak. So it actually goes like this. And so you can see there is a particular omega. So for fixed these values, okay? For fixed, so for some value of RLC fixed, say then there is this particular frequency at which this amplitude is bigger. So suppose I was at this frequency, so omega 1, then it will oscillate between plus and minus say I1, and if I am at omega 2 here, then it's going to be oscillating at I2. But if it's omega 0, so say this was at omega 1, omega was omega 1, and this was I1, so it will go between I1 and I1 amplitude. And if I'm at omega 2, then it might change also here, maybe of course the period will still be 2 pi over omega 2, and this is 2 pi over omega 1, but now it's going to be oscillating between I2 and minus I2. So it's gonna be, a signal will be very small, right? But if I'm at omega 0, then period will be between this guy and this guy's period, and I'm gonna have to kind of devise something now here. So let's see, it goes through some here. It's going to be a bigger, so it's going to be between, let's call this guy correspond to I3. It's going to be between I3 and minus I3. So this is actually the largest I can get for this RLC fixed. So omega 0 is, it turns out that the value of omega 0 is a special frequency at which it oscillates the largest, and so we call it at which current resonates. And this phenomenon is called resonance, and this is called resonance curve of current. Different property will give you different curve. For instance, if I do power, it will be similar to the current in this example, but you know, suppose I wanted to know if I took a voltmeter and I wanted to stick the voltmeter around here, and I want to see what's the voltage reading here, that will also oscillate, and its curve will be a little different. Okay, so different properties will oscillate and have a different resonance curve that usually is not mentioned in the introductory books, but you can work out resonance curve for any property, and some property may not resonate, right? But the current will resonate, and so this property is called resonance frequency of current. And we usually don't write down of current, but because we worked out for current, we should say we only see the current resonate. So this is the frequency of current. If I do a power curve, it will also resonate at this frequency in this case. Okay. So resonance frequency is actually equal to 1 over square root of LC. And sometimes you can memorize it and things like that. Okay. So this circuit is called resonant electric circuit. It has a resonance frequency. Current resonates. We talked about when current resonates, what will happen. You can already see here from the Z that the smallest Z will be when this guy is 0, because both of them are positive numbers, and this doesn't depend on frequency. This is the only difference frequency. So this equal to 0. So smallest Z will occur when omega L minus omega C, this square is 0, this term is 0. And that means omega equals to 1 over square root of LC. Of course, you're going to have a plus and minus here, but I just writing the positive frequency. Okay. All right. So how do we solve to actually, where does these conditions come from, and how do you get these guys? On several ways to do it. And I will illustrate to you a really simple way of doing it. So let me clean up and show you how this curve can be generated. Okay, this curve can be generated, and this formula can be obtained from working out circuit equation for this. Okay, so you already know we can go around in this circuit and write out the equation of motion, which will so this voltage E0 cosine omega t, and then over here the voltage will drop to L di dt, and this will be minus R I, and this will be minus T1 over C I t prime dt equal to 0. So this is going to voltage, right? Now if you take a time derivative, this will become minus omega sine omega t, and then this is going to be minus L d square I dt square minus R di dt, and this is 1 minus C I equal to 0. Well, let's put these guys on the other side. So and manipulate this, and I'm going to get this d square I dt square plus R over L di dt minus 1 over LC I equals to minus E0 times omega over L sine omega t, and I can write this in a cosine omega t, and you can write that E0 omega over L cosine omega t plus pi over 2. So when you expand this, you're going to get minus sine omega t when you expand this guy, right? Cosine omega t cosine pi over 2 will give you 0, minus sine omega t sine pi over 2 will give you minus sine omega t. Okay, I'm doing this because in the last video we said if you learn a little bit of complex algebra, you can actually use it to good practice, and I'm going to try to show you this another good application of that. Okay. All right, so we are you know that this is in inhomogeneous equation. This is an inhomogeneous equation, and so this will have a solution will be I will be some equation where the right side is 0, let's call it IC, and then a particular solution in which right side is not 0, right? So this is solution for the whole thing. Try to fit the, and this one is so IC actually is solves this equation, R over L di c dt, this is plus 1 over LC di and just IC. So you know from this is a damped harmonic oscillator, so let's call R over L as 2 beta. This is also denoted as gamma equals to R over L, and this LC we're gonna say omega naught square equals to 1 over LC. We're just gonna write like this, and then it becomes a simple harmonic oscillator problem. Okay, damped down oscillator. So if you know, solution for this will be IC will have 3 types of solution. So omega naught greater than beta, one solution, omega naught equals to beta, another solution, and omega naught less than beta, another solution. This is the under damped, and this is the critical damp, and this is over damped. And there are 3 different scenarios for this solution. So the first scenario is some and e to the minus beta t and cosine some omega 1 t plus some constant phi. So that's the solution. What is omega 1? Omega 1 is square root of omega naught square minus beta square. And because that is positive, because of this condition, this whole thing is real, and so this thing oscillates. When this is the case, you get same 8 to the minus beta t but 1 plus some bt. So that's the critical solution, and a and b are constants here. And then you get this guy, you get a e to the power minus beta t, then e to the power minus alpha t plus e to the plus alpha t, and alpha is square root of beta square minus omega z square. So this is also real. So this is kind of exploding, this is decreasing, but it's not exploding faster than this is decreasing. So in all of these cases, this goes to 0 as t goes to infinity. So it's actually, and we'll see this one never goes to 0. This keeps oscillating, but this goes to 0 as t goes to infinity. In particular, when t is greater than 1 over beta, ignore. So let's look at what 1 over beta is. Beta is r over 2l. So when then t is greater than l over 2l over r. So I should have written down here 2l over r. 2l over r. So when it's much bigger than that, so we can just ignore this guy. So we just need to get particular solution. Particular solution is a solution of that. And there are two ways to get how to get IP, particular solution. You can say I of t. So one way is do I of t is equal to some kind of a cosine omega t plus b sine omega t, and then solve for a and b. That's one. Plug in there and try to solve by equating, and then lots of algebra there. Second way is that's the one I'm going to list at use complex analysis. Okay, so I'm going to just clean it up and try to use complex analysis. Okay, so you really will like this. Okay, this is, if you put in a little learning of complex things, complex numbers, this is a real treat for you guys. All right, so this is the equation I want to solve. So what are the steps? In the complexification, this thing just cosine, you replace this thing with e to the power I of this angle, omega t plus pi over 2. And then this equation gets replaced by E0 omega over L on the right side. So the left side, you got to generate e to the power omega t, right? So you assume IP to be some constant A, which is complex now. So A is actually A1 plus IA2, or you can write A e to the power I phi. So you can write, so the A is just square root of, if the relationship between these two is just A1 square plus A2 square, and tangent phi is A2 over A1. So that's the relationship between them. And if I know this, I can get A1 will simply be A cosine phi, and A2 will be A sine phi. So we are going to use this notation, a complex notation. Let's do it out. So this is some A, which is, I'm not specifying it yet, and most likely we're going to use this for A, and then it's going to be e to the power I omega t. So the I omega t, this will naturally generate that, and it will cancel out, and then I'll just have a constants left to manipulate. So when I do this, we have a minus omega square, two derivatives, and we can also just use this as a 2 beta and this as omega naught square. Okay, so plus I2 beta omega from here, and from here I got just omega naught square, the whole thing A common. You can work it out. I'm just skipping some steps. And the right side is just going to be E naught omega over L e to the I pi over 2, which is actually just I. E pi over 2, e to the power I pi over 2 is that point in the imaginary axis, which is just I. So this cosine pi over 2 plus I sine pi over 2, and you can see this is 0 and this is 1, so this is equal to I. So this is just I. So this one just is I. And so here the only thing not known was A, and this just solves for A, but you say got to generate our magnitude and phase, right? So A, which is the amplitude of the current, is going to generate I E naught omega over L, and this whole thing minus omega naught is omega square plus I 2 beta omega plus omega naught square. Because we have written down this way the answer, let's denominator work out this way. So take this guy over here, and so this will be omega over L. This will be omega over L. This will be omega over L, and we can kind of simplify it. So one of the omega got cancelled out, so this one is minus omega L, and over here you can see omega naught square was 1 over LC, this guy, and this is omega over L. So this is L cancels out, and this becomes plus 1 over omega C. Let me erase that. Okay, and so this guy is plus I 2 beta was 2 beta is equal to R over L. So this is R over L, omega over omega times L. So L cancels, omega cancels. So this is just IR. So let me clean up that also. Okay, so this is just R. Now, so we got rid of that. So this is now this I can just multiply by minus I here and multiply minus I here, because I just have E0 there. So numerator gets rid of I, and so this thing becomes minus I, and this just becomes 1. So what we have is E0 over R minus this minus plus I omega L minus 1, this minus minus I over omega C. This is minus I, so this becomes a plus, and this, if you can actually include down here, so this whole thing will become just a simple plus 1 over I omega C. So this is the impedance, complex impedance of L, and this thing is complex impedance of capacitance. And so all these things are in a series circuit, as if I replace this with impedance, replace this with R, and this replaces impedance. So this is a series circuit, and just a very simple answer, right? So other than e to the power I omega t, I get the whole thing just handed to me on a platter, just do the calculation in a complex way. So if I write this as E0 over some, so denominator is actually just a Z, total impedance of the circuit. So if I were to say simplify this circuit and say, okay, I got the source, what do I put? One thing, one impedance Z, so that will be the circuit, equivalent circuit for that. And so you get current amplitude of complex amplitude. So this is complex current amplitude. It doesn't have the entire current. Entire current is equal to A e to the power I omega t. So this is complex current, and this complex also amplitude, this one. So this is the whole time. But what we want real part of I. So if this whole thing has to be somehow written as some real part plus I, another real part. So we want this part. So that, and now we're gonna try to extract that. Okay. Okay. So we have this quantity, and you can see that if you might remember from complex lectures, if this is equal to this, then you have a square plus b square e to the I tangent inverse b over a. So denominator we can write as E0 over r square plus omega L minus 1 over omega c square root of that, and exponential I theta, and tangent of theta is omega L minus 1 over omega c over r. Okay, so we can put this on here. So let's look at I is E0 over this thing, which we can call this amplitude of the complex impedance. And so we get an exponential I omega t minus I theta. Or you can just say like this. So you want the real part of this will be just cosine part. So if this one can be written as, say this whole thing is some angle, say A, then this will be cosine, so it will be e to the power IA, and this is going to be cosine A plus I sine B, sine A. We're not interested in that. We're interested in what this is real and multiplies this thing. So it's going to be cosine A. So this is going to be real part will be simply the current will be epsilon naught over the amplitude of the impedance, which is real, and cosine omega t minus theta, which tangent theta equals to that. Seems like there is a difference with what I wrote earlier, and there's a sign problem. I don't know if I've messed up sign someplace, but you can check the sign by assuming a frequency in which omega L dominates. So what happens is, so their domains, if omega L is greater than 1 over omega c, we say it's impedance, is self-inductance dominant circuit. So inductance dominates over capacitance. So in that case, so if you had just this circuit, say if there's no capacitance needed, okay, in that circuit, there is a E leads current. I mean, if I plot the angle, if the E is EMF is this way, this EMF, let's call that E, is in that direction in time. So this is omega t, this angle omega t. Then E will lead by 90 degrees actually. If it's just this, the current will be this way, and they will rotate like that. So if you take some other, say the current was in that direction, then EMF is in that direction. This is omega t, and this whole thing is rotating. This phase is rotating. So we have addressed this in another video. These are called phasor pictures. So over here, you can see that if omega was bigger than L, then phi should be positive. No, phi should be phi is below here, so phi is negative. So tangent, so the theta should be negative. Yeah, so this thing is correct. Okay, this theta should, if omega is greater than L, this theta is behind. Yeah, theta is behind. Okay, so I want to check this. Okay, you should check this. This another way is when this becomes, when would this become negative? You know, if so, this appears to be correct, and it's in the denominator. So in the numerator, it has to be negative. Okay, and so it ends up at negative here with tangent theta that way. So you can change to a phi and flip the sign. Okay. All right, I am done with this video. I'm going to move on to some other circuits which are called coupled circuits next. I've been trying to get to transformer circuits, coupled circuits, and then I think after that I'm going to do what happens when you have a magnetic material. We never really talked much about real magnetic materials, so those things are coming. Have a nice day. Bye.